Charles, this is a great opportunity to talk to you about your career as a scientist, as an anatomist. I thought we'd start by asking you, what was your earliest interest in science, and what do you think were the influences very early?
The very earliest interest in science is the one that I like to tell people about, because it's to do with the importance of a teacher that the teacher may not even know. And when I was 9 years old in Scotland, a little headmaster came to me and he said, "You know, there are some things in this school we don't teach. We teach mathematics, but we don't teach science. You'd better be reading this book." And he gave me Darcy Thompson's book on growth and form. Now, a 9-year-old kid can't understand half of that book, because so much of it, there are Latin quotations in it, Greek quotations, there's logarithms, there are all of these abstruse things that a 9-year-old kid doesn't know. But there were pictures of bones, and there were pictures of bones that had been deformed using mathematical methods. And I thought it was absolutely fantastic. And it was, the die was cast at that point that that's what I would do for my life's work. How about that? It's silly. 9-year-olds.
It's actually amazing, and it's amazing also that the teacher recognized something that he would give that book to you.
Well, it is, and I know why. It's because he had one of those glass cabinets, and he had been abroad, and there was a kris in it, and a kukri in it, and an ostrich egg, all kinds of curios that he'd got from abroad, and I used to spend a lot of time looking at that cabinet and dreaming about it.
That's really neat. So from the earliest time it was science and things anatomical at the same early age? Or
things anatomical. One of the things he gave me to read was something from Goethe. Well, we all know Goethe, that's Faust. But it wasn't to me. Goethe was also a comparative anatomist, and he put forward the idea that the skull wasn't this round thing, that it was a series of vertebrae that had become compressed into a single round structure. And of course he was wrong, but he was very nearly right, because that's how the skull develops today.
And how old were you when you were reading that?
9.
That's amazing.
It was in English, of course. The bit he gave me was in English, because obviously...
So that just continued on then through secondary school?
Yes, I made a major discovery, and it was to do with organisms producing heat. I didn't realise that Spallanzani had made that discovery about 300 or 400 years before.
That's good.
It's, you know, so that one did those. And I can remember very well a situation where I dearly wanted a microscope to look at things, you know, and I was really interested. And the family were having a difficult time with money at that point. And my mother knew I wanted a microscope, but they couldn't afford it. So they got me a hand lens. And it was very interesting, because I was just old enough to understand that the hand lens was not going to do me any good, but also that they had tried enormously hard. And that was fantastic.
They'd gotten you part way there,
yes,
if not all the way there. Yeah. So your parents were very supportive of this then? Yes.
One of the reasons was, of course, that it was a depression, and my father had been forced to leave the grammar school at the age of about 12. And as a result, he felt all his life that he'd missed out on education, and he was going to make damn sure that his kids got it. It was interesting, yeah. Because my mother was a nurse, and that's probably why I became a doctor.
So you have the combination there of supportive parents with some knowledge in that area. That's great. Can you talk a little bit about going on to university?
Yes, I didn't know what to do, because I knew I wanted to do a biological science pertaining to humans. And I didn't know how to do that. And in a small village, who the hell else knows how to do it? And so you scratch your head, and then you say to yourself, well, it must be that you have to do medicine. Because... And so I did medicine, and of course that was, in a certain sense, completely wrong. But in another sense, it was absolutely perfect. And so that's how one got into it sideways from medicine.
So tell me a little bit about that, doing medicine, and how you kind of moved in the science area as well as the medicine area.
Well, I was in science all the time. I mean, almost that first day, I was sitting in the dissecting room, dissecting away as part of the medical course, and the professor comes storming into the dissecting room. He never went in the dissecting room, not the professor. And he looked around and he said, "You, I want you to come and dissect a chimpanzee." Now, that doesn't happen to many medical students. And really, it was that was the thing, particularly as I happened to make a discovery by looking at the chimpanzee. And that was sort of how I came involved in it, and it was also how I came involved in research with him. Now, for a little medical student to expect to do research with the professor, that just wasn't on, especially in England in those days.
And that professor was?
Well, that was a guy called Solly Zuckerman. And that's of interest because a third thing that that little schoolmaster had given me to read was a book called The Functional Affinities of Man, Monkeys and Apes, written in 1934 by Solly Zuckerman. And here I was at the same institution as the guy who wrote the book.
That's remarkable.
That's absolutely remarkable.
So as you were going through then, you were doing medicine and you were doing some of this anatomical research at the same time?
Yes, I was doing the medical curriculum, but in England there was a way of dropping, and you can do it in Australia, and it's not quite the same in the States because medicine is a graduate thing, but there was a way of dropping out of medicine and taking a bachelor's degree in science, and what you did was research. It wasn't courses and so on. And then you returned to medicine to complete it. And of course, once you've been doing some science, you continued to do it and you published and so on. And so the two went pari passu.
So you ended up with degrees in medicine,
in science and in medicine.
As a doctor and as a scientific researcher.
Yeah, yeah.
What happened after that? Where did you go?
Well, I did 2 years of practice. And I did that for a very specific reason. I knew that I would be teaching medical students, and I didn't want to teach medical students without having had at least a lick of practice. And that has paid off in spades, especially when I was in the United States it did, because very few of the people teaching anatomy were medically qualified. But even in England it paid off, because one felt that one knew how anatomy might be used by a clinician. Which you might not have had that if you'd come through the regular PhD route.
So how did you move then from practice into doing science?
That was already foreordained, because working with Solly, it was clear that when I eventually did finish medicine and finish the practice, I would go back to anatomy. And the beautiful thing then happened. It was, of course, that I did not have a PhD, but I didn't get a PhD scholarship. They gave me a postdoctoral fellowship in order to do a PhD. And the money makes a lot of difference. But and in other words, it was because they treated the medical degree as though it were a doctoral level degree, and yet one hadn't had the PhD level training and so on, and so it was necessary to have that. And so that was how that occurred. And then one went into the anatomy department in the University of Birmingham, which is where Solly, in England, not Alabama, which is where Solly was, and I was there for about 6 years. And at that point, you sort of wonder, what are you going to do in life? And there was a problem, and it relates to what has been happening to anatomy departments at that time. Anatomy departments, well, it used to be that the anatomy that was taught was 1,000 hours in 5 terms. And I just escaped that. The year I took it, it was reduced to 600 hours in 3 terms. And then gradually, as you're aware, there's been that reduction and that reduction. And as a result, the anatomy departments, especially those in England at that time, were tending to get smaller and smaller, and there was less and less emphasis on the anatomy, but that also meant that they were losing staff, and there was a greater and greater emphasis on didactic teaching and that sort of thing. Not in Solly Zuckerman's department. When he came there, there were 6 academic staff at the end of the war. He was actually appointed in 1939, but because of the war he never got there until 1945. And when he got there, there were 6 academic staff. When he retired in 1966, there were 54. And that hasn't happened It's happened to some anatomy departments, but very few. And the reason for it was that these were not all anatomists teaching anatomy. There was a psychiatrist, and there was a chemist, and there were 2 behavioral scientists. And in other words, suddenly there was a realization that the science of anatomy wasn't just anatomy, that it had to be something far broader, and that it required the integration of lots of different people working together. And that was the ambience from which I came. And that meant that when it's time to leave, because you don't want to be a member of the staff in a place where you're a student, at least some people do, but I don't think it's very good, you have to go somewhere else. Where can you go? You're already at the best place in England. And so I spent actually a somewhat unhappy 2 years. I'd got a very good friend in London, and he said, look, if you want the readership to Barts, it's yours, because in those days the professor decided who got it. But he said, I advise you not to take it. And he was quite right to advise me that way. And so I sort of wondered what to do, and I looked at Canada, and I looked at Australia. I looked at Sydney, actually, of all places, and I just wasn't right, and perhaps I was slightly too young. I never thought, I knew about the empire, I never thought of the old empire.
The ex-empire.
The ex-empire.
Ex-bits.
And then I was invited to a symposium at Davis with a friend of yours,
which is where
colleague of yours, which is that's where you went,
yes.
Milton Hildebrand.
Yes.
And while I was there, it suddenly dawned on me there were 100 or 120 or whatever the number is medical schools in the United States, and some of them were extremely good. And of course the people at the University of Chicago had their spies out, and within 9 months we were in Chicago.
Before we go to Chicago, can I ask you kind of what your early research, the theme of your early research was before you went to the US?
Well, the very first research that I was doing was indeed sort of almost traditional anatomy. It was to dissect things and to try to understand what was the forms and architectures that you were looking at. And of course it was in the primates. Now I did in fact look at quite a lot of mammals as well. I even dissected a whale, but not the whole whale. but it was the primates, and so it was primate anatomy. But almost immediately it became so clear to me that it wasn't any good looking at that anatomy without trying to understand the function. And it wasn't any good trying to do that without trying to know something about the behavior. Even although in those days, this was before the days of Jane Goodall and all of those people who have been out and really looked at the animals in the field. Almost all that you knew was what was in books and in the museum, not the museums, the zoos and things like that. Nevertheless, it was that functional anatomy thing. And then at that point, something very interesting happened, because the functional anatomy was all based on looking at the anatomy and making almost a guess as to what was happening. Now those guesses were often right, but probably they were also often wrong, and I suddenly realized it wasn't any good doing that guessing. It was no good looking at the anatomy and trying to think what might be happening. What was necessary was to do some experiments to find out what was happening. And that was why I got involved in the mathematical and statistical side. Not that those are experiments, but it's the analysis of data in a way that doesn't obtain from a dissection, but also why I became interested in engineering. And so I took engineering courses in the days before the words biomechanics had ever been invented. I've never forgotten, one of the things was a practical class, and everybody at the practical class came up with pieces of metal of one kind or another, a cylinder block or a lever or whatever it was. And I came up with the bone, straight from the butcher, wet and bloody, wasn't warm, and they were horrified, but they were very excited. And of course the experiments they were doing on their crankshafts, I was doing the same experiments on these pieces of bone.
I was thinking that your approach to anatomy is very mathematical in contrast to a lot of description. I'm wondering, How does that approach, that mathematical approach, change the way you approach questions, anatomical questions, or the questions about how anatomy fits into that broader world?
I think the way that it changes is that if you look at it, you see something. But if you look at it using mathematics, you're rather likely to see the same thing. It would be surprising if you didn't. But you're actually rather likely to see something else that's completely unexpected, that is hidden from you by the naked eye, as it were. And that is the thing that gives you ideas as to what it is that might be happening or what it is that you're seeing. And I think there are probably lots of examples of that kind of thing. And of course this is what harks back to Darcy Thompson, because one of the ways in which he looked at these shapes of bones that he was looking at was to use what are called Cartesian coordinates. And so you put one bone in a grid, a rectangular grid, and then in order to get the other bone, you distort that grid until that bone, now distorted, becomes the other bone. And it was a way of getting a handle on the difference between shapes. Now, he did it with pencil and paper. And actually, I did it with pencil and paper as well, the first time that I did it. But then it became clear that he did it with just the shape, whereas I could do it with the statistical parameters of the shape. And that was when we started to realize that sometimes those statistical parameters were not just a number. They were actually telling you something fundamental about the underlying aspects of the shape. And that's the kind of thing that led to some of the ideas.
So would it be fair to say, or I should just ask it as a question, that not only then is that way of looking at it getting at what's the difference in shape, but how do you get from this shape to that shape? In other words, the evolutionary component.
Well, it's more than just that, because sometimes you get from that shape to that shape because it's the same shape later in time. And so it might be development or it might be growth. Sometimes you get from that shape to that shape, and that one never went from that to that. But both of them came from something else that was much earlier. And so that's a different way of looking at it, and that's the evolutionary way. And of course, obviously, fundamentally, those are quite different things, except that there's an enormous relationship between them, because the evolution of developments gives rise to the evolution.
And I think we'll probably get back to that again before we're done here. You mentioned moving then to the U.S. and to the University of Chicago. Can you talk about the influence of that move and that new environment on your development as an anatomist?
Well, it was really rather fascinating, because I said the University of Chicago had spies out, and I really meant that, because the University of Chicago had only 3 or 4 years earlier had appointed a new head of department, and that was someone called Ron Singer, a totally different character from Solly Zuckerman, but there was a certain similarity, and the similarity was that Ron Singer had the idea that anatomy ought to be something broader than anatomy per se, as you would teach it to a medical student. And so he was looking for people who might, take the department in that direction, those directions. I was very impressed with him for a particular reason. He himself was an anthropologist and anatomist. Now, what normally happens when you get a new professor in a department like that is that they start to fashion the department in their own image. A neurobiologist will put all the emphasis on neurobiology, and that may be very good, because he may be a good neurobiologist and it's good. Ron Singer didn't do that. Ron Singer set out to strengthen all the other parts of the department first. And so he really did things to strengthen, as it was called in those days, cell biology and neurobiology and so on. And the last area that he started to fill was his own area, of which I was in. And I think I learned a lot by that. And it was almost a similar thing to what occurred in the anatomy department in Birmingham. It is the notion that there have got to be interactions among the various people, and that maybe those interactions, maybe they lead to improvements in the teaching, and I hope they do, but they surely lead to improvements, to differences, to opening up in the researchers. And so, although the growth of that department was not as great as Solly from 6 to 54, it nevertheless was a big growth, and it was this rather special kind of growth, and it was highly successful.
Thomas Kuhn's structure of scientific revolutions.
I knew you'd come to that.
Yes. Kuhn argues that people who are trained in a different discipline and then move bring in a different perspective because they're not grounded in the same dogma, so their glasses, so to speak, their filters are different, and that's what really explains really big changes in an area of science. Do you think that's happened in anatomy, and in what places, what parts of anatomy? I don't think that would be very difficult to generalize about, because of all of the different kinds of anatomy departments and the different things that have happened. But let me go to my particular bit of it. It was almost the reverse that happened to me, because I came up as an anatomist. Okay, I had some medicine, but I was an anatomist, you know. And what happened to me was that I saw problems that I realized I couldn't solve as an anatomist. And you would scratch your head and think, well, I've got this problem of the intricate structure of bone, of the internal structure of bone, particularly the cancellous bone. How am I going to tackle it? And then one of the things I always used to do was go to other universities and see what was going on. And so I went to the Department of Geology in Kansas. And of course, the government and oil companies are willing to pay a lot of money to find out how oil flows through rocks. And so there are a lot of these little interstices in the rocks, and the oil goes through it. And they were using a particular method to analyze it. Don't forget, this is 1960s. And what they wanted to know was, what was the pattern of all of this? And the moment I saw a thin section of a rock, I just knew that bones were better. Bones had all of these things through them, and they were using a laser to understand the structure of these rocks. And they were willing to show me how to do it. And so I had to read a lot of optics. I had to read Fourier and mathematics in order to do Fourier analyses of the structure, internal structure of bone. And I did that, and you had to use a laser. I've never forgotten the piece of equipment that I needed. I asked the dean, I said, I'll need a room to do this in. He said, well, what is it? And I said, well, I need an optical bench, and it's about 30 feet long. And he said, oh, I know exactly what to do. And he put a wall down a corridor. My machine was in one half of the corridor, and the other half of the corridor was there. No occupational health and safety, you understand. No wheelchairs could go down that corridor. Now, of course, and it really worked. It was excellent. But you would never do that today. And the reason why you wouldn't do it today is it all works. And you could do it with a laser, but you use computational Fourier transforms today, and that's fast Fourier transforms. And of course, one graduated from that to fast Fourier transforms. So there was something which took me from anatomy into geology, into optics, and then into Fourier mathematics. Well, that's such fun. And I've never forgotten at a later stage going, because I used to visit Solly very often, go back to England because we were publishing together. And I went back to him one time and he asked me what I was doing, and I said I got this problem of the pattern inside the bones. And I told him how we were having a go at it. And he said, you know, it's such a pity. You're out of date. And I said, what do you mean? He says, well, and don't forget that Solly, in addition to being a professor of anatomy, was also chief science advisor to the government in England and had worked a lot in the United States. He was always meeting people like McNamara and people like that, in other words, defense and so on in the United States. And he said, there's a lot of this sort of work already being done. It's all classified in defense, and I can't tell you about it. But it's just what you want. I mean, what a thing to tell me.
But, and he was right. And later on, in fact, I saw this method used for discovering how a tank, how you can identify when a tank has gone through the undergrowth in a jungle. And you do it by taking a photograph of the top of the jungle from a plane and using these techniques to analyze the texture. And lo and behold, the damage caused by the tank underneath has effects on the pattern at the top, and this very technique was used for that purpose. That was only one of the things. I mean,
I think in terms of this whole idea of other training, though, we might be able to explore it even more in your career, because with your knowledge about growth in particular, you've had a different look on some of the evolutionary paleoanthropological sorts of questions that have come up.
How can I best explain it? These fossils that have been found in Flores, and they're very small. They're about 3 feet high. I should say the one skeleton indicates the person's about 3 feet high, and got a small head, and looks like it's some kind of primate. And indeed, not everyone, a lot of people have said this is a new species, but it's allegedly only 18,000 years old. So that's instantly extremely interesting. And it happened that the year it was discovered, I was traveling. And when I was traveling, I happened to meet up with Ralph Holloway, who is the brain guy. He looks at endocasts of skulls and says things about brains. And he said, come up to my bedroom, he said. And he wanted to, this was a scientific meeting, he wanted to show me the endocast to see what I thought of it. And he showed me this endocast. It really was very small, and we looked at it and so on. And I sort of had a view about it, and we talked about it. Then later on that trip, I got a chance to go to the Science Museum in South Kensington, and there they'd got the skull that the endocast had come from. But of course you couldn't touch it, it was in a glass case, but I must have spent about an hour at that glass case. I have a feeling that the people around were getting slightly suspicious, and I looked at that from every possible side, and I could look at it from the top, and I had great difficulty to look at it from underneath for obvious reasons. And so when I came home, the students asked me, well, what did you do? And I told them what I'd seen of this thing, this fossil. Not that I'd handled any of it, although I had handled the endocast. And they said, well, what do you think? Well, I said, I have a feeling that it really has to be another species. It looks so different from humans, and it's about the size of an Australopithecine. And do you think that it can't possibly be an Australopithecine because that's African, but was there something around? And the only problem is it's only 18,000 years, and Australopithecines are millions. So it's very, very curious. And I even wrote a note about this for the students, so it was put on paper. However, I didn't take it any further. And then a little while later, something happened, and it was remembrance of times past. You see, when I was a medical student in 1952, there were still some cretins alive in England. Now, there were no cretins who were born after 1900 because everybody knew about iodine, you had to give iodine to the mother and so on. But cretins can live to be 70 or 80 years old, so there were still some there. And so it was part of the curriculum. I'm sure it's not part of the curriculum today in a medical school. And as I was already at that point interested in bone, I became interested in cretinism, and that these are individuals who are born often without a thyroid, the mother having not had enough iodine and so on, and as a result of it they don't have the thyroid hormone and they don't grow properly, and they end up maybe a foot or a foot and a half, 2 feet sometimes, and they've got small heads and small brains. Some of them, however, are able to live, and they're not very bright, hence the politically incorrect use of the word cretinism, but nevertheless they can live a life. They know the name of the family dog. They don't know the name of the Prime Minister. They're blessed. So in other words, so that they can manage. And I started to look at, and I've got to say that I was doing this with Peter Obendorf, a colleague, and we started to look at cretins, and we suddenly realized that the shapes of cretins were different to the shapes of unaffected humans. A child is smaller than an adult, and it's different proportions, but those proportions change the adult. But the proportions of a cretin are quite different because of the pathologies of growth. And we started to look at this, and then we managed to find a number of cretins in Switzerland, but they occur in other countries, of course. And then I found a bunch in skeletons. Yes, skeletons in museums, and a bunch more in Edinburgh, and so on. And they're scattered all over the world, and in fact, you get cretins all over the world. But in the OECD countries, you only get skeletons in museums. In Southeast Asia, in China, in large parts of Africa, large parts of South America, the cretins are still being born because the appropriate things are not done to prevent it. Anyway, having done all that, it suddenly occurred to us that, was it possible that this was a cretin? You see, and nobody liked that, because for starters it wasn't a new species, and there's nothing worse than putting the kibosh, trying to put the kibosh on somebody's new species. It infuriates anthropologists. But it seemed as though, you know, it's a possibility, and like Sherlock Holmes, you explore all possibilities, and so we seem to explore it. And so we've continued to do that, and the more we explore it, the more we find that suggests that we might be right. But it's still all up for grabs, and it'll be very interesting to see how it washes out.
Do you think you would have come at that, or that would have occurred to you at all, though, if you hadn't had the medical training, different
no, I've got to say that the initial idea probably did come from Peter Obendorf. But when it came to me, it came to prepared ground, because I already knew about cretinism. And so instead of just saying, oh, rubbish or something like that, I thought, oh, maybe, is it possibly right? So it was the seed in the prepared ground. And the seed itself came from Peter, and the very beginning of it. But it's, and of course it goes on. The more we look at both the cretins, we've never been able to look at the fossil. In fact, that's just not been allowed. However, that turns out that's starting to matter less and less, because the people who are describing the fossil, more and more they're actually putting the data out into papers, and therefore you don't have to measure it yourself. They've got the measurements, and then you can, so you can see.
This is going in different order than a chronological order, obviously, but I'm trying to think about the things in some sort of logical way. And your comments about working with Peter and working with Solly Zuckerman and some of the other comments you've made bring to mind the variety of topics that your students have worked with you and that you've been involved in. And I just wonder if you want to talk a little bit about how it is that you have had the finger in so many different kinds of pies.
I'm not quite sure why, in that sense. I can say, though, that when I've had graduate students, I think many graduate students don't know what they want to do. And the person who's a supervisor very often proffers them a project. And it's almost inevitable, if you do that it will be a project that will be related to your own work. And that's not bad. That's not at all bad. In fact, it may even be quite good, because you're probably not capable of picking a project until you know how to solve one. So you can solve one that you've been given, and then you can pick the next one yourself, and so on. But I guess I've been lucky enough to have a number of students who came knowing what they wanted to do. And so, for example, he wasn't my student. He was a student of another member of the faculty at Chicago, but I was involved with him a lot because his project was anatomical, and he was interested in whales. And this was Jim Mead, who later became a curator, or whatever it's called, at the Smithsonian or somewhere like that, curator of whales or mammals or something. And it was absolutely fascinating for me to see the project that he was working on, and in particular, how what he was interested in was how whales, how they projected the sound out, and how the sound came back into the ear. And that was just a fascinating project, which meant that it was necessary for me to dissect a bit of a whale myself, otherwise I wouldn't know what was going on. I had another student, so that's far from human anatomy, I had another student who eventually went to California, and she was interested in chameleons. Well, I don't know, a chameleon from a... I mean, I used to irritate her because I had my classification of life. My classification of life was humans, non-human primates, non-primate mammals, and plants. Everything else was a plant. So chameleons, as far as I was concerned, was a plant. But it was really rather fascinating. Now, obviously, if I was going to supervise it, I got to know something about chameleons, about their evolution, about their anatomy, and she was interested in functional things in them. And so again, one became into that. And another student of mine was working with bats. And it was... now, that's in terms of the animal. But there are other things where what one got involved with was the technology that the student became involved with. So I had one student in Los Angeles who was Vietnamese and couldn't actually speak English when he first came, but he could speak mathematics. And he was great with mathematics, and in particular, he was great with mathematical analyses of mechanics and a thing called finite element analysis. But he wanted to use it to look at bones, and that, in fact, it was through him that I was first introduced to finite element analysis and the ways in which one can understand the mechanics of bones and joints and muscles by using this kind of engineering technology. I've told you already about the laser thing, and that was a technology, but it didn't just involve the geologists at the University of Kansas. It also involved a student who was doing an MD and a PhD at the same time in Chicago. And so he became fascinated by this, and it was through him, really, that I was enabled to take it further myself. And so the technologies, different technologies, the different animals, and then the different kinds of problems that one's been interested in, developmental, evolutionary, and so on.
It sounds to me, as I listen to you talk about this, like the breadth and all of the variations with the different sort of focus and things that you weren't initially very individually involved in has been very exciting to you. And it still is. I mean, people normally retire. Well, of course I did retire. I retired about 15 years ago. But all that has happened is that I now do more of what I enjoy, because I do research 100% of the time, and I teach whenever they ask me, which is not very much, and I do no administration. And that, there are 2 points there. One is that I'm still excited by the research, and it becomes new, it's new stuff. And the other is that governments and administrations of universities and so on have no idea the damage that they cause to academia because of the enormous loads of administration that are placed upon the staff. So I can do research full time. The staff can't nowadays. That was a perfect lead into my next question, which is whether you think that that sort of breadth, that sort of responding to a student's interests and variations therein is still possible in today's academic world.
Well, it happened to me yesterday.
You're retired.
No, it happened to me yesterday. In the sense that Beck is suddenly interested in the tails of kangaroos and how they work. and suddenly I've realized there's something very interesting going on there. But to go to the broader aspects of the is it possible today in the general theme of things, in some ways it is enormously more possible today than ever it was before. Because before, the kind of research I did, it was often a single person job, or a two-person job, or a three-person job. And if there were two of you there, you were both anatomists. You just were bringing slightly different, you were discussing it between you. But nowadays, the nature of problems are such that you can't answer the problems with one background. It's just so that for a lot of the work that we do now, it requires biomechanics. And so it's absolutely essential that we're working with somebody like Michael Fagan at the University of Hull, who is an engineer. It's absolutely essential that we're working with people who are mathematicians who are interested in that kind of thing. Nobody can nowadays answer those problems by themselves. I can't do the engineering part of it. He can't do the biological part of it. But between the two of us, we can. And this is now more and more the case. And one laughs a little bit at these papers in astronomy, which have got 55 authors, because all these different people have contributed to a very large machine. What shall we have? What shall we say? But in fact, that's really the way it's almost got to be. And that's one of the reasons why the old-fashioned kind of anatomy had to go. It just has to be something broader if one's going to be doing research that is near the cutting edge. And I think this applies to all of the aspects of anatomy. If you go into areas which in my day I might have called histology, because you see, cell biology had not been invented. Only just I took the first course in cell biology, and molecular biology certainly hadn't been invented. And as for DNA, who knew about that? Nowadays, you can tackle the kinds of problems. You can be interested in something in muscle, as indeed Miranda is in our department here, and suddenly you realize that you need to know about growth. She needs to know about growth. She asks me about it sometimes. I can almost never answer her. But you need to know about the molecules, the factors, the chemistry, and you can't do it with one person. And even you can't do it with well, you can do it with a team, but sometimes it needs people from several teams to bring in. So this is the way it's changed. And it's fascinating. In some ways, I wish I was at the beginning. The things that I wanted to do 50 years ago, you can now do it.
Yes. At the beginning, you get to do lots of research, it sounds like, and at the end, you get to do lots of research. But in the middle, there's all the other things.
There's administration.
So Charles, while you were in Chicago, and then after that in your career, you had a large body of work that was based in or related to China. Can you talk about that a little bit?
Yes, it really stemmed from a colleague, Peter Lisowski, who was one of my teachers in that first year in 1952. And they said, go west, young man. And so I went to Chicago and Los Angeles and Western Australia. His people must have told him to go east, and he went to Ethiopia and Hong Kong and then to Tasmania. And it was while he was in Hong Kong that he got me involved with the examination of the medical students and so on. But that then took us into China. This was shortly after the Cultural Revolutions. That'd be about 1978, 9-ish. Not very early. In the very early stages, it was the big people from Washington who were able to go into China. But perhaps 3 or 4 years after that, academics could go into China. And so we did that. And the first time that I went as the Chinese Anatomical Association decided that they would invite foreigners. Their definition of foreigners was 6 people from the University of Hong Kong, because of course Hong Kong was a British colony at the time. And as I was an examiner for Hong Kong, they chose to include me as one of the foreigners from Hong Kong. And so we went there, and then I got to know people there, and I got to see places. So I went to Kunming, and there's a primate center there, and so I saw the non-human primates that were there, the golden monkeys and those kinds of creatures. And I also met Wu Kang. And Wu Kang was the doyen of Chinese physical anthropologists. And we worked together, and in fact we produced 2 papers. One of them was in Nature. But this was absolutely fascinating to be into China so early. One saw it was a time when foreigners or visitors were really quite rare, especially not so much in Beijing, but when you were outside. And so if you were in Chengdu, and Chengdu was a very large city, but it wasn't really, it was an enormous number of villages all joined together. And you go in the streets, and of course, I've never forgotten this man who was making toffee on a big tray. And he had coloured toffees, and he was doing this with it and so on. And there were 30 or 40 people gathered around him, all watching. And at the end, he stuck a piece of wood into the toffee and held it up. And it was the most beautiful fish in colours, 2-dimensional fish. And of course, everybody applauded. The thing that was funny, however, was that we sort of looked around. And there were 30 or 40 people there, and they were not looking at the fish, they were looking at Peter and I. And they would come up to you and they would touch your clothes, because of course it was the Mao jacket, and that kind of cloth was not available. And as for seeing somebody who was young with a beard, because at that time my beard was brown, that meant that they had real problems deciding, because they have to decide who you are. And in the end, I discovered that they'd given me a name. Now, Peter was 10 years, 12 years older than I was, and clearly well into middle age, getting on, whereas I was obviously a pretty young academic, probably about 35 or something. But my name, the Chinese name that I was given, was Lao Yetze, or in Cantonese, Lo Yeye, which means the old grandfather. And there are 2 ways of saying that. One is that damned old man. But the other way, and this is the way they meant, is a reverential way. It's reverence for age and wisdom and so on. And so that was fun. But of course, the science part of it was the opportunity to see all of the teeth from, for instance, from Gigantopithecus. There are 2 or 3 jaws of Gigantopithecus available in China. There are some different kind of species in India, for instance, but there were thousands of teeth. And we had measurements of all of the teeth. And of course, all that anybody had ever done up to them was simply to look at the means and the standard deviations and so on. Well, it was wonderful to have so many measurements, and one could really do multivariate statistics on it and come up with all kinds of interesting things. Like, for instance, Gigantopithecus, if you look at the distributions of the teeth, of the dimensions of the teeth, it's like that. Almost total bimodal distribution, and the difference between the means are very large. So what's that?
I would say sexual dimorphism.
Right. But the numbers of each of the large and small teeth are the same.
That's very odd.
That's very odd, because as you're well aware, as you're a primatologist, you expect a small number of males and a large number of females, and we've got equal numbers of them. So you have to think, well, what was going on in Gigantopithecus? And that's not been sorted out yet. And of course, you can't sort it out by just looking at the odd Gigantopithecus fossil jaws or whatever. It requires that kind of statistics.
And through the time since, you've been involved in collaborations in China, I believe?
Yeah. Because we did some studies of some fossils, and at the time that we did the studies, those fossils were called Brahmapithecus and Shivapithecus. And we wrote about them and we called them that. And the paper was accepted. And probably about 3 months later, everybody decided, no, they were going to call it Lufangpithecus. And that it wasn't 2 species, it was 1. And that this was sexual dimorphism. And there's an interesting story there. I'd love to call that back and give them their right names, but the data holds, the findings are all there and so on.
And that is how science works.
That's how science works, and you get caught, hoist by your own petard.
After you were at University of Chicago, you then moved to Los Angeles, to UCLA, was it?
No, USC. USC, private university.
Yes. Can you... What was the kind of motivation for that move, and did it change kind of the themes of your research at all?
Well, first of all, there have been several of those moves: Birmingham, Chicago, Los Angeles, and Perth, Western Australia. And inside those, there were intermediate moves in that each of the times I was there, I spent the first half of the time being an academic, a professor doing research, and the second half of the time being an administrator, but a special kind of administrator who was enabled to keep the research going by virtue of the presidents of the universities being willing to allow it. The reason for that was that in those days, having an administrative position it didn't preclude doing other things. You could do it out of your back pocket to some degree. Nowadays, if you're a head of department or a head of a school or a dean, you can't do any research. You're snowed under with administration. So those were three big geographic, 4 geographic changes. Each time that occurred, it coincided with an enormous burst of creativity. And then halfway through, one slipped over to giving service to the institution in an administrative role, but still being enabled to keep the research going. And that also, paradoxically, gave rise to another burst of creativity. I could go to the dean's office in the morning, and as I walked across campus at lunchtime, all of that rubbish went out of my head, and I did research in the afternoon. So that was absolutely great. Then that leads on to the particular question you answered. In Chicago, I was lucky enough, and I say lucky, to be asked to give service to the university as dean of the college. This was a liberal arts college. Now, with my background, that is, in education in England, you would have said that I wouldn't have been interested in that because, you know, if you want to be a doctor, you take biology, chemistry, and physics, and that's it. Nothing else when you're at school. In America, it's not like that. You know about liberal arts, and many of the people who are listening to this know about liberal arts and general education. And when I went to Chicago and I was asked to do that job, I totally bought the American idea of general education. I think it was wonderful. And so I enjoyed an intellectual difference for that reason. And so at that point, when I was asked to be dean of the graduate school at USC, I thought, well, graduate schools are different from colleges. Let's have a go. And I did, and I had a wonderful time. And then after I'd done my term, because if you do this in the old way, it's service to the university, you give your service and you stop doing it. There's a good point about that. If you're going to return to being a professor, then you make the kind of decisions as an administrator that are good for professors. That doesn't happen nowadays. And then the same thing happened here. I came here and I was head of department and so on. And then they changed the structure of the university and they needed an administrator, and so I became head of science and agriculture. And that was fun.
That leads absolutely into my next question yet again. This is a slightly different kind of question. I'm interested in what you would say is the most for the better change that you've seen in academic and research environments, and the for the worse change that you've seen over your career.
Let's go to the worst one first. There are quite a number that you could go to, but I think the one that upsets me the most is to do with the careers of academics. I never applied for a job in my life because they were so short of people that you would be invited to take a job, and a lot of the time you didn't take it because you can't keep changing all the time. But that was wonderful, to the freedom that to be invited to take a job, to know that one's career is going to continue. all of those kinds of things. This is really one of the reasons why one made those kinds of moves. Today, unfortunately, I see a situation where the young people find it extremely hard to get jobs. They may find themselves, they do a PhD, that's research. If they're lucky, they get a postdoc, and that's research, and they're on soft money. And then, well, they haven't got a job, so they take another postdoc, if they can get it, and they're on soft money. And it must be devastating to their thinking, the thinking part of their careers, to be continually having to worry about where the money comes from, where the money for research is going to come from. And in a lot of cases, it doesn't come. And the people leave. There's all that story about PhDs being taxi drivers in New York, but there's a great deal of truth to all of that, and it's very, I find it very sad. And those are not just stories. One knows of so many people to whom that's happened. So that's one of those sorts of things. But I think one of the really good things that's happened is the intense excitement that you can get from the kind of research that I'm describing, which brings you into contact with all these different kinds of people and different kinds of ideas. Ideas that you couldn't have got by yourself. It's almost as though you're stealing. But it's a legitimate stealing. It's allowed, as long as you say where it came from. And it's the kind of stealing where people steal from each other and back again. And that kind of stealing builds and builds, and it really takes you into places, and it is so exciting.
Given the changes that you've seen and the research and academic world as it is, what advice do you have for young PhD students, or even younger, or postdocs in the general area of anatomy or comparative anatomy?
Well, I've got a number of different pieces, I think. Let me think. One of them is to take heart. You see, when you're doing a PhD, there are long periods in a PhD when the PhD student is so depressed. The work doesn't seem to be going anywhere. They don't quite understand what they're doing. It seems terrible. And then, with luck, they get themselves over it. Maybe their supervisor helps them to get over it. Maybe someone else helps them to get over it. Whatever it is, hopefully they get over it, and that's all right. After the PhD, the reason for that is that they're tackling one problem, the PhD problem. After the PhD, they may in fact discover that they're tackling 2 problems, or 3 problems if they're lucky enough to get that far. And after that, they suddenly find that their interests have broadened and they're now tackling a big bunch of problems. And then one realizes that there's a gastronomical description that one can apply to this. The one problem, and I think everybody should have this range of problems. The one problem, the one set of problems are what I would call bread and butter problems. Okay? Bread and butter problems are the kind of problems which you probably know what the answer is going to be. You do it, and lo and behold, that is the answer. But you've advanced science a bit because you've found something new. But it was fairly obvious, but there we are. And that's good. And lots of people do that kind of research. And it's good. It's sort of earth-shattering, but you're learning things. And then it's a good idea to have some other kind of research. And I would call it cake research. You remember Marie Antoinette is supposed to have said, if there's no bread, let them eat cake.
Let them eat cake.
Well, cake research is the kind of research that is not totally obvious. It really is harder to tackle it. But it's much more interesting, and you're rather likely to get an answer you do not expect. And that leads on to others, and that's extremely exciting. And that probably is what most of your research should be like. But the other bread and butter ones may be important because they may be parts underlying the cake work. You need to know some simple things in order to look at the more complicated things. And then, of course, I think it's important to have 3 or 4 projects that are pie in the sky. And of course, those are projects that are utterly hopeless. They're not going to work. If by chance they work, you get a Nobel Prize. And you should have some of those. And it's hard to know what to do with them, because in one sense, when you've got one of those kinds of things, which obviously are not going to work, you'd think it would make sense to stop doing it and put your efforts somewhere else. And that may be sensible. But then again, for some individuals, when it's clearly not going to work, it may be that in fact, nevertheless, you persevere and persevere and persevere, and 20 years later it does work. And you get an enormous surprise, and then you really get a Nobel Prize. But in other words, it's that kind of distribution of ideas and ways of doing them. And this, of course, doesn't just apply to the one individual, it applies to the one's relationships with other individuals, with students, with colleagues, and so on.
How long have you been doing that?
Well, 1952. When I was in Birmingham, and especially when I was in Chicago, one of the things we did was have coffee. Everybody has coffee. And at coffee, some of the academics would be there and some of the graduate students would be there, and what we talked about was research. At a much later stage, 30 years later, when we had coffee, the graduate students and the academics would be talking about jobs. And it was very important to talk about jobs, but it was a terrible loss to the intellectual thinking. And so, very interesting.
Over that time, when you think back over the things that you've done, the projects you've done, is there one or two that really stand out that you feel the fondest of? It's your preferred scientific offspring, so to speak.
Well, there are two answers to that. The one is the kinds of things one saw, really liked, because you got a totally new view of things. And the other is the things that I've done, which have turned out to be heresies. And I love those because something occurs and your colleagues tell you you're nuts, and it's not accepted, and so on. And that has happened to me 3 or 4 or 5 times during my life. And the beauty of it is that the first one it happened to, probably about 20 years later, people started to realize that maybe it was right. They didn't always recognize it, where it had come from, but nevertheless, that has happened. And that's happened, one of the very first ones was to do with the Australopithecine, and the idea that they were absolute human bipeds and absolute human ancestors. And now, although there are still some people who think that, I think the great majority of people recognize that they were on side branches that went extinct, and that they were not human bipeds in a modern human manner, that they still climbed and did a whole lot of things like that. And that's, you know, I was saying that probably in 1965, but it's been at least 20 years before that sort of changed. And of course it still hasn't changed for many people, and it certainly hasn't changed when one looks at the lay views of human evolution, where this thing is cast as a direct human ancestor. Then you can go a bit further, and one's been interested in bone and the way in which the structure of bone is related to the stresses and strains that it bears. And again, in the early days, there was a very simple answer to that, and it was really that it was to do with tension and compression, acting on bone and so on. Then it becomes more and more complex, because it turns out that the picture you see in bone in 2 dimensions cannot be generalized to 3 dimensions. And when you look at it in 3 dimensions, it's actually quite different. And so the 2-dimensional view looks good, but it's wrong. And I'd taught that for 50 years to medical students, but I don't do it anymore. So there are lots of things like that that have occurred.
Kind of ugly duckling ideas that become
yes,
swans.
But not too much. Of course, what I'm waiting for, I'm waiting to live to be 100 because by the time I'm 100, it's just possible they may have realised that Homo floresiensis, the fossil from Flora, is a cretin.
With that, looking forward to being 100, I'll ask the last question I have for you, which is, what unfulfilled aspirations are you still working on? Do you have any?
Well, yes, but I'm not really. I am working on them, but these are aspirations that I can't actually do. They require collaborations with other people. It may sound as though this is the same as it always was from what I've been saying, but for example, there are some things that are happening now in terms of the biomechanics of bones and so on, which I know what to do, I know how to do it, and I cannot do it. It requires the nimbler mind of younger people, and so we have these collaborators, and some of them are graduate students, but a lot of them are academics, professors, but they're just that much younger than me, and they're able to do that, and I'm in on it. I contribute to it. I contribute especially in terms of ideas. One of the reasons is that I still know the anatomy, and they have often forgotten the anatomy. And it turns out that the anatomy is still important in looking at those things. So that's one of the and there are a lot of sets of things. That's the biomechanics. There's an exactly similar thing occurring with the statistics. In the beginning, it was called multivariate statistics, and then it started to be called morphometrics, the measurement of shape. And then it became called the new morphometrics. And of course, I was the person who helped to set the old morphometrics going. The new morphometrics evolved out of it, and I couldn't do the new morphometrics. But then I met people like the people in Vienna and the people in York in England and various other groups of people who were doing the new morphometrics, and I got intercalated into it. And I still can't do it, but I can pose the question and they can do it, and it's a genuine collaboration, and it's absolutely fascinating. And the third thing is not to do with those at all. It's to do with the fact that one writes papers and it's fun, but more and more, and this may be a sign of increasing age, it may mean that I'm going downhill, or maybe it doesn't. It is that I'm becoming more and more interested in the bigger picture. And so I'm really interested in looking at things where one writes a book and tries to put together different, quite disparate kinds of things. And of course, I have just written a book, and it's got a wonderful title, and I'll tell you what it is, because somebody might buy the book and contribute to my royalties. But the title, you see, is Ghostly Muscles, Wrinkled Brains, Heresies and Hobbits. And if you can think of how I've woven those things together, you can see that it's a fun book. But it's not, it's got a lot of research in it, but it's not new research in that sense, like a paper. It's a more synthetic kind of thing. And that's one of the reasons why I'm still getting a great deal of pleasure out of teaching, so that my teaching is much more synthetic, perhaps, than it was before.
It sounds to me like you haven't slowed down at all. It's just in some small areas the role has changed.
Well, some of them are big areas.
Well, this has been fascinating. Thank you for the opportunity,
Well,
Charles.
thank you for
really
asking the
enjoyed
questions,
it.
Deborah.